Kubernetes can turn one update into many moving parts. Here is the big idea: Kubernetes is not just a place to run containers. It is a control system that decides, stores, and repairs what should be running. Let's meet the main players we'll keep reusing. The control plane components make decisions, and the worker node runs the workload. First, the API server is the front door for every request. We can think of it as the one place where the cluster accepts and validates changes. Next, etcd sits behind the scenes as the source of truth. It remembers the cluster state even when the machines restart. The scheduler watches for pods that need a home, and the controller manager watches for drift. Together, they turn intent into action. On the worker side, the node runs the pod through kubelet, while kube-proxy handles service traffic on the machine. That is how requests reach the right workload. A user change goes to the API server first, because that is where the cluster receives the desired state. The scheduler then uses that stored request to choose a worker node. It is like assigning a delivery to the best available driver. One common mistake is to think the node decides everything by itself. In reality, the control plane decides, and the node carries out the work. Let's trace one request. Kubernetes works like a busy restaurant front desk. You hand in one order, and several specialists coordinate behind the scenes so it gets cooked, tracked, and served correctly. First, the API server is the front desk. Every request enters here, and every other component reads or writes cluster state through it. The scheduler is the matchmaker. It looks for a worker node with enough room and picks where the new pod should run. The controller manager is the steady hand. If the desired number of pods drifts away from reality, it notices the gap and asks for repairs. etcd is the record book. It stores the cluster's desired state, so the control plane can always check what should exist. On the node, kubelet is the local worker. It receives the pod assignment and makes sure the container actually starts and stays healthy. Kube-proxy handles traffic on the node. It steers network requests toward the right pod so clients can reach the app reliably. The client sends the request to the API server first. That is the only doorway the control plane needs to expose. The scheduler sends the placement decision to the chosen node path. It is not starting the container itself, it is assigning the job. The controller manager compares desired state with live state. When something drifts, it sends a correction request back into the system. etcd feeds the control plane with the saved cluster state. That stored truth is what keeps the whole system consistent. The kubelet launches the pod on the node after receiving the assignment. It is the component that turns the plan into a running workload. Kube-proxy forwards incoming traffic to the pod endpoint. That keeps access stable even when the pod moves or changes. Traffic spikes fast. A photo-sharing app can go from calm to crowded in minutes. One pod is just one running copy, so it can become the bottleneck when everyone uploads at once. Here's the wrong instinct first: just create a second pod by hand and hope it stays that way. The right approach is to let the deployment and ReplicaSet manage the copies for us. The ReplicaSet watches the number of pods and fills gaps when one disappears. That means if a node fails or traffic grows, the app still has the copies it needs. The deployment sits one level above that and manages change over time. It can move us from V1 to V2 gradually, instead of replacing everything at once. This table compares the three core objects. The columns are object, job, and real-world meaning, and the pattern is simple: the higher we go, the more automation we get. Think of it like a movie theater. A pod is one seat, a ReplicaSet keeps enough seats filled, and a deployment changes the seating plan without chaos. So during the traffic spike, we do not babysit individual pods. We declare the desired state once, and Kubernetes keeps reconciling until the cluster matches it. Stable access starts here. A pod is like one coffee cup on one counter, while a service is the pickup number that stays the same even when the cup changes. The left side is the moving target, the right side is the stable address people use. That stability matters because users should not chase changing pod IPs. The service gives us one doorway, even if Kubernetes replaces the pod behind it. Now let's place the key pieces on the board. The service is the front door, kube-proxy lives on each worker node, and the pod is the app running behind the door. Next comes the node side. Kube-proxy watches service rules and programs traffic handling on the worker node. Here is the worker node that runs the workload. The pod sits on the node and can be replaced without changing the service address. Finally, this pod is the actual app instance. It may come and go, but the service keeps pointing to whichever pods are healthy right now. Traffic enters the service first. From there, Kubernetes sends it toward the node-side routing rules. Kube-proxy forwards the request to a healthy pod on that node or across the cluster. The arrow shows the actual traffic path to the running app. Here is the key misconception to avoid. The service does not run your app, it only gives stable access while pods do the work. Controllers keep this relationship healthy in the background. If a pod disappears, the controller replaces it, and the service automatically keeps sending traffic to the new healthy pod. Now we wire app settings. On the left, the config map holds non-sensitive app settings like the theme and API endpoint. On the right, the secret holds the API key, which the pod can read without hard-coding it into the app. Think of the pod as the running weather app container. It starts with both pieces of input, so the same code can show a dark theme in staging and a light theme in production. The deployment sits above the pod and keeps the app updated. If we change the image version, it rolls out a new pod set without us rebuilding the settings by hand. Here's the important rule: ConfigMaps are for non-secret configuration, and secrets are for values we must protect. We still need good access controls, but the object choice keeps the intent clear. This table compares the two objects by what they store, how the weather app uses them, and the main caution. Notice that both feed the same pod, but only one is meant for sensitive data. So the pod reads configuration at runtime instead of baking it into the image. And the deployment keeps the app version moving forward while those settings stay separate. Quick check, let's test the core pieces. Here's a quick check, read the options and pick the best answer. The correct answer is etcd and scheduler. etcd stores the cluster state, while the scheduler chooses which node should run each pod. The API server accepts requests, but it does not store the state itself. Now let's anchor the other two ideas. So if you see changing pods behind one stable name, think service. And if you see app settings without passwords, think config map. One last trap to avoid: secrets are for sensitive values, while config maps are for plain configuration. Let's wrap it up. First, the control plane is the brain. The API server accepts changes, the scheduler picks a node, the controller manager keeps desired state, and etcd remembers the truth. Then the worker node does the hands-on work. The kubelet starts and watches pods, while kube-proxy helps traffic reach them through the cluster network. Finally, the objects fit together like layers of responsibility. A pod runs the app, a ReplicaSet keeps the write count, a deployment manages updates, a service gives a stable address, and config maps or secrets feed in settings. If you remember one sentence, make it this: Kubernetes separates control from execution so apps can move, scale, and recover without us babysitting every container.